就拜拜。
hello，拜拜啊，好，OK，喂，让我看，你要让我看，
把它用掉。
这样他们可以看，你看我拜这样啊，这样拜拜。Okay, let us explain a bit more about this. All right. This is all right. That's, for example, this is my first 5-second data. All right. That's my first 5-second data. I use this data to form V, to compute alpha and beta, compute T, A, B. I compute alpha 1C, alpha 2C, alpha PC, and beta 1C, beta 2C, and beta 2C, the PC. So this set of data going to allow me to compute alpha beta and alpha 1, alpha C, and beta C, all these numbers. Then after 5 seconds, I turn on. I turn on control force. So this control force, when I turn on this control force at K, then I need K minus 1, K minus 2, as K minus P. If P equal to 2, then you need only K equal to minus 1 and K minus 2. So I need only, for example, this is my, K is my 5.01 second. For example, all right? Then I need those data before 5.01 to 02 seconds. So you may not use this data anymore. This data will be new data after you turn on the control force. And this UC, this UC came as 3. So when you are UC, you will be able, you need to use your new UC, not this U. This is for system ID U. This is for control force U. Okay? So when you compute this UC, the first at 5.01 second, you might use some of Y here. Not that much, because it only up to P equal to 2 or 3 or 4 or 5. So if P equal to 2, you use only past 2 data. Now all this. Understand now? As soon as you turn on UC, you will have a new data come in, new output, new input. Then you use a new data, new output, new input. And this is become O1. That's for system ID only. Okay? Understand now? Okay. Yeah. So if you have a question you ask in the class, it was easier because I can explain to everybody. If if you only ask me personally, then maybe some other people has the same questions. Okay, let us talk about Cobra stick model. If you look at these pictures, this did not look like a Cobra. But when we do simulations, that we just simulate the Cobra environment. We call simulate Cobra environment. For example, we have a shackle here. This is a shackle. We saw shackle, which will shake this beam here. And then we have this looks like a propeller, and this looks like the hub. In other words, the Cobra stick model, the Cobra, they have some external disturbances, and this is the external disturbances we simulate. So we have external disturbances from here. Then we have a control force from some other shackle, and then we have the accelerometers distributed in this beam there. Okay, that's what we call Cobra stick model, and we use this predictive control we call GPC to control the Cobra unstable model. The Cobra, in matter of fact, in many cases, they are unstable. All right, the same thing. If you look at this, the first 0.6 second, do you see that first 0.6 data? The first 0.6 second here. We have a control input, give them control input. And then we have the called tail boom vertical accelerations. This is the output. And this output includes the output introduced by control force, but this control force is very small. So these responses, most of the responses come from the disturbances, the unknown disturbances. Just like I show you the 3 mass and spring model, I have some external disturbances. That's all. Those are periodic disturbances. So the first 0.6 second, I have input, I have output, just like I show you in the simulations. All right. Then I allow them a little time to do system ID, to compute alpha beta, to compute TAC, to compute alpha C, beta C, and then I can compute my control force and turn on at the 0.7 second. So as soon as I turn on my RUC, I use the new data for my output and input. And you can see that as soon as GPC on, see, response is reduced. So it take about 0.1 second to reduce the responses to a very small value. Of course, your control force, you still have a control force there. Look at this control force. And it's a sign, it's a periodic control force. Then you still have output. That's a periodic output, because you still have disturbances, the periodic disturbances existing still there. And those periodic disturbances for Cobra model really come from the aerodynamics. Now you understand now the process? Okay, this is exactly the same process I show you for that 3 spring mass and despot example. Any questions? Any questions? So as long as you know the process, this is the way to do it. So you can have a GPC off. That's the GPC off, those off, we need to have a GPC off because we need to have 0.6 second data for us to do all the computation for control force. Listen, only 0.6 seconds. That's less than 1 second. You know why? Because in 1 second, the Coppola model may crash already. So everything we talk about is less than 1 second. So all the less than 1 second means you have to do the system ID, you have to do controller design. 2 steps, right? Okay, so those are the Coppola model, and this is real data. This is not simulation data. Okay, and let us look at this called XV15. You know, XV15 is like a helicopter when you take off. Then as soon as you take off to some certain, then this propeller, so you take off like a helicopter, you fly like an airplane. Now, the problem of this design is when you lift off, and then when you try to fly like an airplane, you have to rotate those propeller. And when you rotate those propeller, then it becomes an unstable system. When you rotate those propeller, and that's no good, because the aircraft can crash. When your system become unstable, aircraft become unstable. Agree? So, how can you control that? But I don't have model. The same thing. You need to take some data, and then to do system ID, to compute TAB, and then to compute your alpha 1C, alpha 2C, beta 1C, beta 2C, and then use a new data output, a new data control input to control it. Okay, so this is the control input and roll responses. You look at carefully here, because I don't know this XV15 well enough to explain all the physical meaning of this. But however, of this slide is that you have a desired responses for your roll responses. That roll responses mean you want to fly, roll, fly. All right. When you want to roll, then I want to say, can I have this kind of sharp roll? Can I have this kind of sharp roll? Desire sharp roll, right? That's my desire. That's the one I want to do it. But actually, you cannot do that because there's a discontinuity at this corner, that corner. That discontinuity, it cannot achieve that. So when you do real maneuver, you can do as much as I can just the desire one. So you desire one, what we call desire one means you may not reach it, you may not achieve it. That's what we call desire one. Desire one doesn't mean you can always achieve it. For example, if I have a desire eigenvalues, can my pole placement technique will allow you to get a desired eigenvalue? Yes or no? The pole placement, if I have a desired eigenvalues, under only one condition, for controllable system, you can always achieve the desired eigenvalue, but it has to be controllable system. Controllable system means the system is controllable. Some system is not controllable. Even if you give them desired eigenvalue, you may not be able to do that. So you have to be for a controllable system. Yes, the desired eigenvalue are achievable by pole placement technique. But your desired eigenvectors doesn't matter is a controllable system or not. Normally, it's not reachable. Okay. So that's one model. this rat model, and I spent a lot of time in 90s, but from 95 to 99, I spent a lot of time to help to make sure that we can control this called rat model. This is the model from Navy. So when in the laboratory, they designed a very small, or a smaller rotorcraft. We call rotorcraft. Rotorcraft means a helicopter, and I will show you the real pictures of that. And then we know that the helicopter is in a very small region. I will show you in certain RPM, means your propeller stop moving. At about 750 RPM, about 750 RPM, that frequencies, they oscillate with some of the helicopter body frequency. And if they oscillate with the body frequencies, means can be unstable. All right, I will show you the pictures, the photo of that. And this model, how we control? We control the brakes. The helicopter has the brakes, right? The brakes. You know the brakes, right? Then you can control the brake angle. That's the way they control the helicopters. So you can turn the brake angles in certain degree to control the stability of the helicopters. Okay, let me show you that I think this is not important to you anymore, because this is exactly the same what I show you the process, the ID process, and then computer alpha C, and beta C. Okay. The same thing here. The first 1 second. The first 1 second is the time we do system ID. We give them input. The input is what? The input is change the angle of the brakes. All right, and the responses, you can see the responses, they come from some periodic disturbances, unknown disturbances, and plus your control input. And after 1 second, you turn on the controller. And that's the control. Then this is responses. The blue one is responses. So within 1 second, that response is going down to almost to zero. Means your system from oscillation, if you don't have a control, then they will oscillate like that. This is a red line. They'll keep oscillating like that if you don't have the control. If you have a control, then it just go down. And the red one here is your control input. So your control is still working on your control. The red one is your control force. That's on your right. There's a right axis here. You have 3.5, 4.5. Those are control force, the amplitude. And the left one, that's the bending moment. That's the beam. That's the motions of the helicopters. Okay. And the next one. Let me go to the next one. There's a movie here. I want to show you this movie, and then I explain the chart on the right hand side. Okay, you look carefully on this movie. When this rotation speed come up to about 750, okay, they are oscillating. That's the oscillating. Did you see that oscillating? I'll play again. All right. So this the rotor speed is keeping moving up. This is speeding more. Come out to 750, about 750. See, if you don't turn off, that will break. The vibration is too much for the whole system. So when you rotate from 0 to 400, 600, and up to 750, Look at this, the Hall vibration here. That's very dangerous if we don't turn off. That will break. The whole sensor break. And this system costs 500,000 US dollars. 500,000 50万美金. Just a system like that. Small system in the lab costs that much money. So you break it, and it takes a few months to build one again. So, on the right hand side here, this shows you why they become unstable. If this is your roller speed, when your roller speed from 0, 400, 600 to 650, there's one eigenvalue of the system. The one eigenvalue system, the damping ratio, you know the damping ratio, you already learned the damping ratio. The damping ratio going down. The damping ratio going down. Damping ratio is supposed to be positive. Going down to 750 become negative. One of your eigenvalue, your damping ratio, going down from like 1.5% to negative. From 1.5 to 0 at 750. After 750, then below 0. That means unstable. That means that can break. That's why you can see the vibration of this. That means the damping ratio is going down up to 750. Then that damping ratio then at 0, and if you don't turn it off, then it's gone. However, if at about 600 we turn on the GPC, in other words, from 0 to about 500, we use those data for your system ID to compute alpha beta, then compute TAC, then compute alpha C, beta C, and then at about 600 RPM, then we turn on our GPC. Then that eigenvalue will jump from about 0.05 up to about 3. So that becomes stable. You turn on your GPC at about 500 RPM, then it becomes stable. And that's true. This is real data. On the right hand side, that's the real data, and this is real experiments. So 750, all right, becomes stable. See, if you turn on your GPC and last about a second, it becomes stable. Any question about this? The movie is easier to understand, right? So show you the helicopter. This roller speed. Roller speed will change the stability of the system. So next time, if you have a chance to go to ride the helicopters, you gotta be careful. I'm serious. So you need to have a good pilot. A good pilot will avoid that problem. They just simply control their rotor blade angles, and then it's okay. But if you have a GPC built in there, then he doesn't have to worry about it. Okay? All right. So that's just proof to you that the GPC works for the RADS testbed. All right. The same GPC, then we also, because we have such a successful test, and the Air Force like us to do it in the wind tunnel. To do a wind tunnel, the purpose of wind tunnel is we want to see that we can reduce the vibrations of the aircraft due to by aerodynamics. So this wind tunnel, we have a wind going to wind tunnel, right? wind going to wind tunnel just like aerodynamics speed, wind going to wind tunnel. And that will excite what? That will excite the wall of the wind tunnel. And the wall of wind tunnel just like an aircraft fuselage, just like you sit in the airplane, it's upside down anyway. But like that. Okay, so and this is the controller at the wind tunnel wall, and we have the piezo ceramic to be used as the actuator. The piezo, if you charge, if you give them electricity, then they will constrict or expand, and that's the way we control the wall. And we also put the accelerometers around the wall, and that's the sketch here. So we do have this 1, 2, 3, a lot of the point here. Those points we have the accelerometers, and those 1, 2, 3, those are I believe those are the piezo, the piezoceramic actuators, and those are the those is the accelerometers, and those the piece, 1 piece, 2 piece, 3 piece, those are the piezoceramic. So the output we have 1, 2, 3, 4, 5. We have 15 output, then we have 3 inputs. For this case, we have 15 output and 3 input. And those are the modes of the plate, this plate, the modes of this plate, right? This analysis, and this is the real data. This real data show you what? Show you that the two they all. This is show you the sound pressure level dB. There's 2 different marks. One is 0.0, 0.1 is 0.2. The mark is the speed of the sound, and that's 2 different. They excite different frequencies of the plate. So if you look at this, 0.1 excite less frequencies than 0.2. Right, so you mark 0.2, then your frequencies, those higher point, the peak here are the frequencies point, and the solid line is 0.1 mark, and they excite less frequencies. So the higher mark, you excite more frequencies than lower mark. All right, and this is just show you that our system ID. This is from experiment measurement, and this is from system ID. The bar there, that's when you compute alpha and beta, and you can plot this called spectrum, and this spectrum really your ID do a very good job. So this spectrum really match the real data. Okay, when you compute alpha and beta, you can use the alpha beta to plot this we call spectral density. So this is spectral density, and you can see that they are matched very well to your real data. So this is is a real data, measured data. And the same thing, we have no control, you have no control, and 3 actuators, while 1 actuators. And if you have control, your 3 actuator control, 3 while 1 actuators, then you can see that they can reduce the dB up to 9 dB. So for 3 actuators, you can reduce down to 9.86 dB. Now 0.96 dB, so that's a lot of reductions. How much 10 dB is a reduction? Do you know? You know, 40 dB is 100%. 20 dB is about 95. and 10 dB has about 80% reductions. A lot of reductions, but because they require us to reduce only 5 dB. Now we can, for this GPC, we can reduce up to 9.86 dB, much more than required. So that's good sign. So this GPC worked very well, and the same thing here. Okay, and this is real, the real sense, and that's we published this paper too. And this you can see these are supersonic, means the military aircraft. Only military aircraft move more than 1 Mach. The commercial aircraft will be less than 1 Mach. Move more than 1 Mach is dangerous. But anyway, those just a lot of experience. This is Mach 0.8. This type of commercial aircraft. Commercial aircraft, the speed is about 0.8. And the GPC can reduce about 9 dB. The GPC can do that, 9 dB. All right? And for 2.5 Mach, then the GPC can reduce 8.9 dB. So it doesn't matter is 0.8 dB, 9.2, and this is 8.9. It's not bad, right? Because when you have a Mach higher, then you excite more frequencies out. The same thing here, 2.5. You can put about 9.3. This we call multi-bay controller. Multi-bay controller means we have a more piezo plate. This is 0.8 again. All right. This chapter, we conclude this chapter. I think we'll finish this about 7 p.m. So the GPC exploratory studies of GPC for active aeroelastic control of tail rotor aircraft completed in this, and it was very successful results. It had very good successful results. And we include the numerical simulations, like experimental, investigations, multiple input, multiple output. GPC was highly effective in increasing stability and reducing the responses. So this is in the 1990, it's about year of 2000 conclusions, so still good. And NASA still using this GPC, still doing research in this GPC as well. So GPC appears to be a valuable approach for active stability augmentations and vibration control of tail rotor aircraft. Wind tunnel test of RATS model, the helicopter model with GPC need to more fully evaluate model to fully evaluate the methods. And now the NASA is still working on this method too. For any control method before they put in a real practice, you have to do a lot of testing. Can be 10 years, can be 20 years testing before they really put into the aircraft, just for safety. Although now it's very promising, but to really put inside the commercial aircraft require a lot of more research again. Anyway, that's it. So that concludes the predictive control, the GPC, and that also concludes our semesters. Because these semesters, now you learn at least 4 or 5 different control methods. The TMD, right? That's a passive one. The virtual passive, right? TMD, virtual passive, AVA, and then you learn power placement technique. You learn the optimal control technique, you learn the predictive control techniques. So you learn at least about 5 different control techniques. But by the way, these 5 control techniques, they're all we call modern control techniques. Means all in the time domain. It's not frequency domain approach. It's time domain approach. And the time domain approach is easier for the computer implementations. If you use computer to do the control, then you are talking about digital control. If you talk about digital control, then you are talking about like a predictive control. That's a pure digital control. All right? That's a digital control. It involves system ID. You don't have to have a model by yourself. The data will give you a model, and that model will give you alpha and beta. And then from alpha beta, you will compute T, A, B. From T, A, B, you control alpha C and beta C. From alpha C and beta C, you compute your control force. From your control force, then you can control your system. And those are simple steps. And to implement in the control in the computer is very easy too, because only what? Only very simple matrix computations. No integrations, no differentiations, right? So for computer, it's easy to compute the matrix operations. Okay, you have any questions? It's about 7 p.m. If not, that's we ended this class. And I thank you very much for taking this class. And also that I may not be able to see you until next year. All right, this coming semesters, I don't offer any course anymore. And I also encourage you to go to our system, or computer system, to evaluate me, right? 教师评审, you can go to the computer to evaluate me so that I can improve myself to do a better job. So it doesn't matter you like or not, because your name won't be there anyway. You can say yes, you can no, you can criticize me, and you can give me good points too. Anyway, and that's good for me, not just only for you. All right, and don't worry about the final exam. I keep saying that, take it easy, you know. And I always give you exam only when only those problems either in my slides or something I talk about it. All right, I don't exceed those boundaries. And well, we still have a yes and no problems, and also we have some just by hand calculating. You don't need computer to calculate. Hand is good enough. All right, just like a midterm. And if you know all the concept, if you understand all the concept, then you can finish it in 1 hour. As a matter of fact, that's true. The midterm is the same thing. If you understand it, you can finish it in a very short time. And also we'll be in the same class as in the midterm class. All right. Any more questions? No? Okay. Thank you so much. We ended this class. Bye-bye.